What's going on, everybody? It's Mr. Diamond, and we're here in section 2 of chapter 1 over redox chemistry, and we're going to be talking about oxidation numbers. We talked about what redox was in the last chapter, but now we're going to actually assign a value to that. So we know what they are, we just need a way to actually characterize them and keep track of our electrons. So to do this, we use oxidation number. Buried the lead really great in there. It's perfect. Oxidation number is the measure of how many electrons are lost or gained by an atom at a given moment, at a specific moment in time. It's sometimes also referred to as an oxidation state. The most likely place this gets confusing is when people assume that it's equal to an element's predicted charge. This is not always the case. There is a set of certain elements that it is equal to their expected charge, but there are certain elements that you have to look at what it's attached to determine what the charge is going to be. In more complex reactions, determining oxidation numbers can allow us to determine what is being oxidized and what is being reduced without actually needing to draw pictures and try to circle dots and see where they go. In the reactions we're going to look at, however, sometimes they won't be as neat as that. So we can't do that little sketch thing to figure it out. This is going to be a lot more easy on those more difficult problems. So we're going to kind of treat our oxidation number as basically it's like an atomic prenup. It's an agreement between the atoms that if they break up, who is going to get what. In a prenup, you assign what goes where at the ends of a marriage, like money, property, pets, whatever. But they're going to do the same thing, but they're going to be looking at electrons. Also, the marriage can involve a whole lot of people, but don't focus on that part. If the compounds were to split, who would take what electrons? Or more scientifically, who's holding the electrons more and would be the most likely to keep them if the compound broke apart. This is going to have to do a little bit with electronegativity and stuff like that, but we're not going to use our charts. We're just going to be using the formulas of the compounds that we're given. Just like in law, there are certain rules you have to play by. You can't just hold a gun to your fiance's head and then make them sign it and then you get all their money when they die. You have to kind of follow the rules when you're assigning oxidation numbers in the same way. As a usual rule, those with higher reactivity have better lawyers, and so they're going to end up with whatever they want, while the ones with the worst lawyers are kind of stuck to just do whatever the other people in the reaction want to do. One final note is you do have to have these rules memorized. So you do need to make sure that you have these rules memorized. There's only about 5 of them, and most of them are pretty straightforward. So make sure that you have them memorized because you need to know them for the test. Okay, rule number 1, oxidation number of an uncharged element by itself is 0, even if there are multiples of the same element. So Ne by itself has an oxidation state of 0. It's not sharing with anyone, so there's no gain or loss of electrons to keep track of. Chlorine gas, which is Cl2, has an oxidation state of 0 as well. Both of those chlorines are just sharing with another version of themselves. So they're not pulling electrons closer or pushing electrons further away. They're just going to stay equal, so they're going to be 0. So if this was Br2, N2, I2, and if this was any single element, and it could be something even like Na or Fe or O or something like that. O would probably be really weird, but it could just be a solid that we're talking about there. Like a chunk of sodium would be represented by just Na, and that means it would have an oxidation state of 0. Rule number 2, total oxidation number of an atom or compound must add up to the charge of that atom or compound. If it's neutral, they have to add up to 0, but if they had a charge, they have to add up to the charge of that atom or compound. So in O2-, it has an oxidation state of -2. Notice that after I made all of this big deal in Chem 1 about how it's 2- because there are 2 distinct negative charges, oxidation state is actually written as the plus or minus first in the number, because it is a value given to it as opposed to a total of the number of types of charges that they have. I know it's super nitpicky. It really does sort of make sense after you're in chemistry for a long time, but just bear with me. I'm still not going to really count you off if you make that mistake though, so don't worry about it. But if you're planning to go to college, you should probably try to make sure you get that straight. I apologize, everybody. It's been a long day already. It's a lot of videos. Now, in our compound NaCl, for example, our oxidation states must add up to 0 because NaCl does not have a charge. There's no charge right here. That means the two oxidation numbers of Na and Cl separately have to add up together to give you a charge of 0. Rule number 3, fluorine is the most reactive element. It has the best lawyers of anyone at the table, so fluorine always gets what it wants. Fluorine always has an oxidation state of -1 because fluorine always wants to gain 1 electron. The other halogens also usually have an oxidation state of -1, especially when they're paired with metals, but they are not a 100% guaranteed thing, and you shouldn't jump into every problem assuming that. That's why they're not mentioned here. Fluorine is the only one that you get to just lock in immediately. Fluorine is a -1. If you see it, it is a -1 every time. Oxygen also usually has an oxidation state of -2. When paired with fluorine, it does not, and you'll have to determine fluorine's charge first and then figure oxygen out later with some critical thinking skills. The only major exception to that is in peroxide, which if you remember is O2 2-. And in that case, there's two oxygens that added together need to have a charge of -2, which means each one of them must be contributing a -1 to the oxidation number. So oxygen would only have an oxidation number of -1 in a peroxide compound. Rule number, I thought I skipped a number for a second. Rule number 5, there are some elements that are usually a specific charge. Group 1 metals, so that's Li, Na, K, Rb, Cs, Fr. All of those have an oxidation number of +1. Group 2 metals, that's Be, Mg, Ca, Sr, Ba, Ra, all the second column, have an oxidation number of 2+ or +2. And then hydrogen is usually +1. Unless it's attached to a metal. So if it was like NaH or MgH2, in that case, hydrogen would be a negative charge. While their lawyers are not as good as fluorine's for the purpose of our metaphor, they are looking to ditch their electrons, so they're not really competing with each other. It's like if you had sodium and fluorine bonded together. Fluorine's like, and I'm going to take the kids. And sodium's like, yeah, I don't want the kids. You can have the kids. Like, it doesn't matter if fluorine has better lawyers when they're just both trying to accomplish the exact same thing. Also, don't be like, don't be like the group 1 metals and group 2 metals. Don't be like sodium. You should want to keep your kids if you have kids in the future. Don't be a jerk. Okay, so here, based on only those 5 rules, we can now logic our way through this whole set of problems right here. And I'm going to work those out in a separate video. I'm going to switch over to my hand cam and I'm going to work them out. I'm going to do one click to check and see if I have the answers on here or not, and I do. So I am not going to do that for the rest of this video. We'll call the video right here and I'll do those examples. Actually, let me click 2 ahead, make sure. Yep, that'll take us to the end of section 2. We'll talk about identifying redox reactions, which may seem like something we've already talked about, but you'll see how it's related whenever we get to that next week. In the meantime, though, this has been Mr. Diamond. If you have any questions, please shoot me an email. Otherwise, have a great rest of your day, everybody. Hope to see or hear from you soon.